Just a few hours ago, and at the time of making this video, the Nobel Prize in Chemistry was announced. This year's prize went to the hands of Alexei Ekimov, Mungi Bawendi, and Louis E. Bruce for their contribution and discovery of quantum dots. Chances are that some of you guys watching this video might be witnessing this quantum phenomenon right before your eyes. So let's talk about what quantum dots are and how they work. There are some key terms that you may have heard of when quantum theory knocked down your bedroom door and violently woke you up from a peaceful sleep, whispering in your ear. Wave-particle duality, superposition, Heisenberg's uncertainty principle, quantization of energy, wave functions and probabilities, entanglement. As quantum theory leaves your bedroom, you feel dirty and want to take a shower, but you're probably also confused. So let's at least help you with the second part. The term we're most interested in when working with quantum dots is quantization of energy. So let's take a step back and think of particles like a cat chilling on the couch. This cat, recently awoken from its nap, wants to jump in the shelf so it can look down on you and judge you for breathing and being alive. In order for the cat to get on the shelf though, it needs to jump with just the correct energy. Too much and it will fly over the shelf. Too little and it won't make the jump. The cat can only jump on the shelf if it meets the correct energy requirements, and you can think of each shelf having its own energy. What we have just described is quantization of energy. So how does it work in quantum dots? Well, in the context of the shelf, its height can be thought of as the energy requirement, whereas in the quantum dot, its size creates the energy requirement. Let's see why. Quantum dots, as described in the Nobel paper published by the Royal Swedish Academy of Sciences, are neither molecular or bulk materials and constitute a new class of materials known as nano-sized semiconductor crystals. Semiconductors are materials that have intermediate conductivity, hence semi, and an important feature is that they have a band gap between the valence band and the conduction band. The valence band corresponds to electrons which are involved in forming covalent bonds, whereas in the conduction band the electrons are relatively free and can take part in conducting electricity. Thus when electrons go from the valence to conduction band, the material can conduct electricity. Despite this, the energy level of bulk semiconductors are not quantized, meaning that the cat we described earlier can jump to just about anywhere on the shelf. So how do we get quantization of energy in quantum dots? Well, the quantum culprit in this case is quantum confinement. By confining the particles, we're also confining their electrons in all dimensions. This restriction means the electrons can occupy allowed levels of certain energy and can jump to other allowed energies as long as the energy is exact. Thus, by varying the level of quantum confinement, or in other words, the size of the quantum dots, we can achieve different energy gaps. This can best be seen with the figure on screen. Alright, cool, now we have equipped you with the necessary quantum toolkit. It's now your turn to go knock on quantum theory's door, right? Well, slow down there, partner. Let us first explain how these quantum dots are made. We come across a pivotal moment in 1993 when Mungi Bawendi and his dedicated team pioneered a method that revolutionized the synthesis of quantum dots. Their novel approach yielded quantum dots of significantly well-defined sizes and unparalleled optical quality. The synthesis method started with the injection and swift pyrolysis, a chemical process where substances are broken down by a high heat, of organometallic reagents. In simpler terms, these reagents are organic compounds that contain metal, and they act as the building blocks or starting materials for creating the desired nanoparticles. This mixture was introduced into a hot coordinating solvent that had a notably high boiling point. The heat and the reagents combined caused an abrupt supersaturation, akin to suddenly saturating a solution with too much salt or sugar, triggering nucleation or the initial formation of particles at a precisely defined moment. Accompanying the injection was an immediate temperature drop and dilution of the precursors, the original materials. This acted like hitting the pause button, effectively halting the growth of these nanoparticles. But here's the interesting part. After reheating to the right temperature, a systematic growth process ensued within the coordinating solvent, which ensured that the resulting particles remained stable in their liquid environment. The next step was like sifting for gold. Through purification processes, the best particles with the most desirable properties were selected and harvested. And indeed, the result was akin to striking gold, a bounty of nanoparticles that not only had a consistent size and shape but also had special surface properties that made them extremely efficient in interacting with light. Ever looked at the rich hue on a QLED TV? That's quantum dots in action, manipulating light with size-driven color emission, making our entertainment visually electrifying. As we previously discussed, in quantum dots, the size of the dot dictates these energy levels. Smaller quantum dots have electrons with higher energy levels. When excited, they emit light towards the blue end of the spectrum. Conversely, larger quantum dots have electrons at lower energy levels. This results in light emission towards the red end when excited. In the medical world, quantum dots are pioneering advancements that seemed almost fantastical a decade ago. Let's delve deeper. Cancer surgery has always been challenging. One of the biggest hurdles, distinguishing between healthy tissue and cancerous ones. But quantum dots are changing this narrative. These nanoparticles can be engineered to bind specifically to tumor cells. Once bound, they can be illuminated using specific light wavelengths, causing tumor tissues to glow. This luminescence offers surgeons a clear visual distinction between healthy and cancerous tissues. The result? Enhanced surgical precision, minimize damage to healthy tissues, and increase chances of completely removing cancerous cells. This method holds immense promise for improving patient outcomes and reducing post-surgical complications. Thinking bendable? Quantum dots are also shaping the future of flexible electronics. Traditional electronic components are rigid, limiting their applications. Quantum dots, due to their nanoscale size and ability to emit light, are excellent candidates for integrating into flexible substrates. By embedding quantum dots into polymers or other flexible materials, we achieve electronic devices that are not only bendable, but can also display information or change properties based on inputs, all while retaining their functional integrity. Imagine a future where your wearable tech adapts seamlessly to your movements, or screens that roll up, all thanks to the flexible nature empowered by quantum dots. And sensors? They're evolving, but how do quantum dots play a part? We can look at a brief example of a QD sensor from the paper done by Vilner et al. Here they use quantum dots as sensors for pesticides. On screen, we can see an enzyme known as anti-acetylcholine esterase, ACHE, which happens to be part of a catalytic cascade that produces hydrogen peroxide, H2O2. The QD sensor is modified to be avidin capped, and the fluorescence from the quantum dot is inhibited by hydrogen peroxide. In the presence of pesticide, however, ACHE becomes inhibited, and hydrogen peroxide concentrations become lower, allowing for the QD to fluoresce brighter. By increasing the concentration of pesticide, we can achieve better fluorescence as shown in the plot. Overall, this allows us to use quantum dots as chemical sensors. And with that, you have come to the end of this video, and we would like to thank you for watching. Let us know in the comments if quantum dots deserve to win the Nobel, or if it should have been handed to another discovery. Be sure to like, subscribe, and share with all of your friends and family. We will see you guys in the next one. Bye bye.